So we're already up to lesson 19. It's the 19th day. There are only 28 days in a semester, so we have 10 more classes. And we're going to spend, as I said, the rest of the semester learning about group theory. We spent a lot of time looking at certain classes of groups. We looked at symmetric groups. We looked at matrix groups. We looked at the integers and groups of congruence classes. And several times I've also mentioned cyclic groups, especially finite cyclic groups. And so it's always good to have examples, but what we are now studying is what is called group theory. This means properties that anything that's a group satisfies. So from the very, very, very short and simple axioms that define a group, there's a very rich theory. And all of these things, permutations, matrices, integers, congruence classes, finite cyclic groups, they all satisfy these things. And very often you have things which superficially look different, but deep down are really the same. So in algebra, when we say two things are the same, we mean what is technically called isomorphic. And I defined on Monday a homomorphism and an isomorphism. And I'm going to do it again because it really is so important. So let G and G prime be groups a function f from G to G prime is a homomorphism if it satisfies one property. F of xy is f of x times f of y for all x and y in the group G. And again, as I keep repeating, I will generally use multiplication as my group operation. But if you have a group where the group is addition, you change the times sign to a plus sign. And again, notice x and y are in G. So this is multiplication in G. But f of x and f of y are in G prime. So this multiplication is multiplication in G prime. And there's actually a kind of a nice picture of this. It's a diagram. So suppose we let G cross G. This just means the set of all ordered pairs, x, y, where x and y are both in G. This is just the set of ordered pairs. So we have the following picture. We have a function from G cross G into G. What is this function? This is just multiplication in G. You take a pair of elements and you multiply them and you get an element in G. We also have G prime cross G prime. And we have a function from G prime cross G prime into G prime, which is multiplication in G prime. And we have a function from G to G prime, a function f. This sends an element x to the element f of x. And from G cross G to G prime cross G prime, we have a function which we might write as f cross f. How would you define it? If you take a pair of elements x and y in G, you want to get a pair of elements in G prime, you let this be f of x prime, comma, f of y prime. So that's this function f cross f. And what does it mean to have a homomorphism? If you take an element xy in G cross G, you can get from here to here by going in two different ways. You can go across and then down, or down and then across. So if you have x, y, and you go down, you multiply them, you get x times y. And if you go across, you get f of xy. Take a pair in G, multiply it, you get xy, and that goes to f of xy. Or you can go across, xy goes to the element f of x, comma, f of y. And when you multiply these two, that is when you go down, you get f of x times f of y. And what does it mean to say you have a homomorphism? A homomorphism means this is equal to this. So the fact that you have a homomorphism means in this diagram, if you go across and then down, you end up at exactly the same element in G prime as if you went down and then across. So to understand algebra at a somewhat deeper level, perhaps, it really is good to try to understand this picture. So that's what a homomorphism is. A function f from G to G prime is an isomorphism. If first, f is a homomorphism, f is 1 to 1, and f is onto. So let me give an example of an isomorphism. Suppose we let G be Z mod MZ. This is the additive group of congruence classes modulo M. And how is addition defined? Well, we know addition of congruence classes. Say x plus b, x plus say A plus mz, that's a congruence class. B plus mz, that's a congruence class. And you add them and you get the congruence class of A plus B plus MZ. So that is addition in the group of congruence classes modulo M. Suppose we let G be gammas of M. This is the cyclic group of order M. So G consists of all powers of a fixed element. Let me call the element, I don't know, U. This is all powers of U to the I. I goes from 0, 1, 2 up to M minus 1. That means, well, I'll call it X. So this is the identity, X, X squared, X cubed, up to X to the M minus 1. And this is a multiplicative group with the following multiplication. X to the I times X to the J is equal to X to the I plus J. No, actually, it is equal to X to the I plus J, which is also equal to, but if I plus J is greater than or equal to M, this is X to the I plus J minus M. And the fact that this is a cyclic group of order M means X to the power M is the identity. So we have an additive group of order M and a cyclic group of order M, and I claim that they're isomorphic. So I claim that the integers mod M, this is an additive group, is isomorphic to the cyclic group of order M. And this is the symbol for an isomorphism. Proof. Well, in order to show that two groups are isomorphic, I have to construct, first step is construct a homomorphism F from Z mod MZ to gamma M. So, and how do we do this? As follows. You let F of the congruence class A plus MZ be equal to X to the power A in the cyclic group of order M. So this is in Z mod MZ, that's a congruence class, and F of that congruence class is this element in the cyclic group. So what do I have to show? In order for this to be a homomorphism, I have to show that if I take F of A plus MZ plus B plus MZ, F of the sum of two congruence classes is the product of their images, F of A plus MZ times F of B plus MZ. Okay. This is in the additive group, so there's a plus sign. This is the binary operation in the multiplicative group, so there's a times sign. Okay. Are there any questions about this? This is, you know, if you grew up thinking that mathematics is about numbers, now you realize you were misled. There are numbers in mathematics, but it actually makes up a very small part of mathematics. Well, let's see. So f of a plus mz plus b plus mz. This is the proof of this statement. This is f of, if I add these two congruence classes, I get the congruence class a plus b plus mz. That's equal to x to the a plus b. But x to the a plus b is x to the a times x to the b. And x to the a is f of a plus mz times x to the b, which is f of b plus mz. And that's exactly the property that I needed to show. So f is a homomorphism. F is onto because any power of a, of x to the a, any power of x, is f of the congruence class a plus mz. And f is 1 to 1 because if f of a, let me write it on a separate page. So remember we have f from z mod mz to the cyclic group defined by f of a plus mz equals x to the a. So if a plus mz and b plus mz are congruence classes modulo m, and if f of a plus mz equals f of b plus mz, then this is equal to x to the a, this is equal to x to the b, so x to the a equals x to the b, which means if I multiply by x to the minus a, I have x to the a equals x to the b, multiply by x to the minus a, this is x to the a minus a, which is 0, this is the identity, and this is x to the b minus a. And x to a power is the identity if and only if a is congruent to b mod m. If and only if the congruence class of a plus mz equals the congruence class of b plus mz. So that's the proof. So this is a pretty, and I would say pretty important example of an isomorphism, that the additive group of congruence classes mod m is isomorphic to the finite cyclic group of order m. Any questions about this? No. If you look at the notes that I posted, section 5 on homomorphisms has a lot of properties of homomorphisms, and let me state some of them. So properties of homomorphisms. So again, we have a homomorphism F from the group G to the group G prime. Suppose we let E be the identity element in G and E prime the identity in G prime. So this is a little theorem, which is in the notes, I think is theorem 12. It says, first of all, F applied to the identity in G is always the identity in G prime. And second, if I take any X in G, if I take F of X and then the inverse of that, that's the same element as if I took X, took the inverse of X in G, and then applied F to that and got F of X prime. So these are two properties of a homomorphism. Proof. So if E is the identity, that means E is certainly E times itself. So F of E, E is the same as E times E. Because F is a homomorphism, this is F of E times F of E. Multiply, I don't know what F of E is, but every element has an inverse. Multiply by F of E inverse. I get F of E inverse times F of E is F of E inverse times F of E times F of E. And by associativity, this is F of E inverse times F of E times F of E. Because F of E inverse times F of E, that's E prime. F of E inverse times F of E, that's E prime times F of E. And multiplying anything by the identity just doesn't change what you're multiplying, F of E. So this says F of the identity in G is the identity in G prime. So this uses just the definition of a homomorphism and the definition of an identity. You should really take a look at this for a minute or two and convince yourself that it makes sense.
I have a question.
Sure, go ahead.
So about the end, when we have E prime, and we have, like, I couldn't understand the last part.
This
From
last
multiple.
equation,
Yes.
is this what you're asking about?
Yeah.
So E is the identity in G. So E times E is equal to E. Is that okay?
Yes.
So F of E is the same as S of E times E, because these two elements, E is equal to E times E. And because F is a homomorphism, F of a product is the product of the F's. So this is F of E times E is F of E times F of E. And what do I know about F of E? All I know is it's some element in the group G prime. right? E gets mapped to something f of E in G prime. And everything in a group has an inverse. So so that f of E inverse, this is the inverse of f of E. So I take this equation and I multiply it on the left by f of E inverse. So I get f of E inverse times f of E. F of E inverse times f of E, that's this. But that's the same as f of E inverse times this, because they're equal.
Oh,
This equals this equals this.
okay, got it. Thank you.
Right? And then by associativity, this is the same as f of E inverse times f of E times f of E. And every element times its inverse is the identity. So this is the identity times f of E, which is f of E. So if you look at this long equation, E prime equals f of E. And that's what I wanted to prove.
Okay, got it. Thank you.
Sure. And what about the second statement? I want to show that if for all x in the group G, if I take f of x in G prime and take the inverse of that, that's the same as if I took x, took its inverse in G, and then applied f to that. So the proof is as follows. We know that E is equal to x times x inverse, because an element times its inverse is the identity. So f of E is f of x times x inverse. Right? I'm just applying f to this element. I just proved that f of E is E prime, the identity in G prime. And by the property of a homomorphism, f of a product is the product of f of x times f of x inverse. So if I multiply this equation by f of x inverse, I get f of x inverse is E prime times f of x inverse, because the identity multiplying something doesn't change it. But the identity, let me write it on this side. F of x inverse is f of x inverse times the identity. That's f of x inverse times f of x times f of x inverse. And by associativity, this is f of x inverse, oops, this isn't wrong, but it's not what I wanted to say. I want to say, do exactly what I said. I want to say, I want to multiply by f of x, the inverse of f of x. This is what I'm doing. So f of x inverse times E prime is f of x inverse times f of x inverse. By associativity, this is f of x inverse times f of x times f of x inverse. An element times its inverse is just the identity. This is the identity times f of x inverse. So this is f of x inverse. And here I have the inverse, that's what this is, of f of x. So this and this, they're equal. So that's the proof. again, it's very hard to understand the details of a proof when you see it during a lecture. You really need to write it down or look at the notes where it's written down very legibly, and really study it at home. It takes a lot of time to understand this. So I always like to draw pictures of things. So let's say this is the group G, this is the group G prime, and I have my function f from G to G prime. So for example, if I take the identity in G and the identity E prime and G prime, E gets mapped to E prime under F. In fact, there can be more things. I mean, there can be many things in G that get mapped to the identity. So what is called the kernel of the homomorphism F is the set of all points in G such that f of x is equal to E prime. It's everything in the group G that gets mapped to E prime. So this is what is called the kernel of the homomorphism F. And by the previous theorem, we have that f of E is E prime. So E is certainly an element of the kernel of F. Now the kernel of F has several very beautiful properties. So the first is the kernel of F is actually a subgroup of G. If I look at all the elements of G that gets mapped by the function F to the identity, that actually forms a subgroup. So we have to show three properties for a subset of a group to be a subgroup. The first we've already shown, namely the kernel of F contains the identity, because F of the identity is the identity. We have to show that this is closed under multiplication. That means if X is in the kernel, let me call the kernel K so I don't have to keep writing a lot. If X is in K and Y is in K, then X times Y is in K. This is what I have to show. But the proof is really easy. So if X is in K, that means f of X, let me do it on another piece of paper so I have more room. So again, we have a homomorphism F from G to G prime, and K, which is the kernel of F, is all elements in G that get sent to the identity in G prime. And we know, first of all, E is in K. Right? I just proved that. Second, that X be in K and Y be in K. What does that mean? If X is in K, f of X equals the identity, and f of Y is the identity, E prime. And what is f of X times Y? Because F's a homomorphism, this is f of X times f of Y. That's E prime times E prime, which is E prime. So therefore, XY is in K. So this shows that K is closed under multiplication. Finally, we have to show that K is closed under taking inverses. We have to show that if X is in K, then X inverse is in K. And how do we prove that? If X is in K, f of X equals the identity, which means f of X inverse, which I proved was the inverse of f of X, but f of X is E. That's the inverse of E, and the inverse of the identity is the identity. So X inverse is in K. So that's the proof. Any questions about this? And in fact, there's even a stronger statement we can make. So we have F from G to G prime a homomorphism with the kernel of F, I'll call it K. If X is in K, and if A is any element of the group, then AX A inverse is also in K. And the proof's as follows. What is F of AX A inverse? Because F's a homomorphism, this is F of A, F of X, F of A inverse. F of A is F of A. X is in K, so F of X is the identity. And F of A inverse is F of A inverse. So this is just F of A times F of A inverse, which is the identity. So the kernel also has this property that if you take any element in the kernel and you multiply it on the left by A and on the right by A inverse for any A in the group, you still stay inside the kernel. Yeah. So let's pause for a minute just to take a look at all this, and I'm happy to answer questions if there are questions. So this operation, which we just performed on an element of the group, has a name. So let G be a group, and let A be any element of G. Let's define a function, I'll call it gamma sub A, from the group to itself as follows. Gamma sub A of X is equal to AX A inverse. And we call this operation conjugation by A. And gamma sub A, it's a function from G to G prime. I'll make this a little theorem. This function It's a homomorphism, but it's not only a homomorphism, this is always an isomorphism from the group to itself. So how do we prove this? So you have to show, first of all, that gamma sub A of xy is gamma A of x, gamma A of y. That's the definition of a homomorphism. So what is gamma sub A of xy? That's A xy times A inverse. So this is A x times y times A inverse. I can certainly put the identity in there. You can always multiply by the identity. But the identity can also be written as A inverse times A. So what we have here, we have AX A inverse times AY A inverse. This times this. And this is gamma sub A of x, and this is gamma sub A of y. So gamma A is a homomorphism. Let y be any element of the group, and let x be A inverse YA. Then gamma sub A of y is AYA inverse. That's the definition of conjugation. What is, so gamma sub A of x is AX A inverse, but this is x, A inverse YA times A inverse. And A times A inverse cancel, that's the identity on both sides. And we're left with y, which means gamma sub A is onto. For every y, I found an x where gamma A of x is equal to y. And if gamma A of x equals gamma A of y, then AX A inverse equals AY A inverse. If I multiply on the left by A inverse, I can cancel the A's. If I multiply on the right by A, I can cancel the A inverses. So x equals y, which means gamma sub A is 1 to 1. So this operation of conjugation by the element A is a homomorphism. This is from the group to itself. No G prime over there. This is just G. Gamma A is a function from the group to itself, and it's a homomorphism. It's onto and it's 1 to 1, so it's an isomorphism. So this is another very nice example of an isomorphism of a group. Okay. Any questions? Okay. Let's go back to our picture where we have a function f from the group G to the group G prime. Here is G, here is G prime, and there's some function f between them. Here's the identity. Here's the identity. And we had all the elements in G that get mapped to the identity. This is the kernel of F. But we can also look at any other element. I mean, take any element X, it gets sent to F of X. And so because we're really mapping all of G into G prime. But it doesn't necessarily cover all of G prime. It's just maybe some subset of G prime. And the name for that subset is the image. So if we look at the element f of x, where x is an element of G, and we look at the set of all these things, all these red points over in G prime, that is called the image of F. So the image of F is everything over here that in some sense comes from something back in G. Here's a simple example. Suppose I define the function from the integers to itself by f of x is 2 times x. So here we have z, this function f from z to z. 0 goes to 0, 1 goes to 2, and so forth. What is the image? Well, the integer x goes to 2x. Everything in the image is even. So this is all the even numbers. So for this function, the image of f is the set of even numbers. If you have an odd number, it's not in the image. 1, 3, 5, and so forth. This is not in the image. So here we see the image of f is a proper subset of the group Z. So that's a very elementary example, but it's a good one to keep in mind. And just the way the kernel of a function is a subgroup, we also have that the image of f is a subgroup of G prime if this function f from G to G prime is a homomorphism. So you have G being mapped to G prime by some function f, which we're going to say is assume is picking a homomorphism. And if you look at everything in G prime that comes from something back in G, that's what's called the image of f. And I claim this is a subgroup of G prime. So what's the proof? Well, the first step is easy. F of E is equal to E prime. So E prime is certainly in the image of F. The identity always goes to the identity. So the identity in G prime is always in the image. So if Y and Y prime are in the image of F, then that means Y is F of X and Y prime is F of X prime for some X and X prime in G. And that means that Y times Y prime is F of X times F of X prime. but that's f of x times x prime. That's an element, xx prime is an element of G that f maps to yy prime. So y times y prime is in the image of f. Any questions about this? So there are three properties that need to be checked if a subset of a group is a subgroup. It has to contain the identity, which the image of f does. It has to be closed under multiplication, which the image of f is. And it has to contain the inverse of each of its elements. So let me just prove that. So let y be in the image of f. So that means there exists an element x in G with f of x equal to y. And then y inverse, well, that's the inverse of f of x. What I proved the inverse of f of x is f of x inverse. X inverse is in the group, f of x inverse is y inverse, so y inverse is in the image of f. So let me prove one or two more properties of a homomorphism. So we have a homomorphism f from G to G prime. The theorem says that f is 1 to 1 if and only if the kernel of f, which we know contains the identity, in fact contains nothing else other than the identity. So if the kernel of f is this trivial subgroup consisting just of the identity, then the function, the homomorphism, is 1 to 1. So proof. Suppose K, which is the kernel of f, is not just the identity. Then there exists an x in the kernel, which is not the identity. But what does it mean to say x is in the kernel? That means f of x is the identity in the group G prime. But f of E is also the identity in G prime. If you take the identity in G, it gets mapped to the identity in G prime, which means I have X different from Y, but they get mapped the same thing. So that means F is not one-to-one. So if the kernel of F is different from the identity, the function, the homomorphism F is not one-to-one, or the contrapositive is F one-to-one implies that K, the kernel, consists of just the identity. So this is the left to the right part of this if and only if statement. Right? I just proved that. If F is one-to-one, then the kernel is the identity. What about in the opposite direction? Suppose K consists of just the identity. Take two elements in the group such that f of x equals f of y. I want to show that f is one-to-one, so I must show x equals y. Two different elements can't be sent to the same element in G prime. So from this equation, multiply, let's say on the right, by f of y inverse. I have f of x equals f of y, multiply by f of y inverse. So what I have, f of x, y inverse, that's f of x times y inverse, is f of x times f of y inverse. F of x is equal to f of y, it's f of y times f of y inverse. F of y inverse is the inverse of f of y. So that's E prime, which means xy prime is in the kernel, because f of xy inverse is in the kernel, because f sends xy inverse to E. But the kernel, our assumption is the kernel consists just of the element E. So xy inverse equals E, multiply on the right by y, x equals y. So f is 1, 2, 1. So this gives a very important criterion for a function, for a homomorphism to be one-to-one. It's one-to-one if and only if the kernel is the trivial subgroup consisting only of the identity. There's also a kind of subgroup criterion for a homomorphism to be onto, but it really is just the definition. So, but I will note it down. Again, we have G prime, this function f, E goes to E prime, but if you look at everything that G gets mapped to, we have the image of f. This is all y in G prime, such that y is equal to f of x for some x in G. And f is onto if and only if for all y in G prime, there exists x in G with f of x equal y. That is, for any point y in G prime, I can find some x in G, which gets mapped to that y, if and only if the image of f is all of G prime. So this is really nothing more than the definition, but a function is a homomorphism is onto if and only if the image is all of this group G prime, which is the range of the function. Now, there are lots of homomorphisms that you know. So here are some examples. Homomorphisms. You can take the function f from the real line to the positive real numbers. So this is the additive group of all real numbers. Right? You know you can add numbers. This is the multiplicative group of positive real numbers. For the additive group of all real numbers, the identity under addition is 0. For the multiplicative group of positive real numbers, the identity is 1. So what's an example of a homomorphism? F of x equals e to the x. Your beloved exponential function from calculus. This is a group homomorphism. Why is it a group homomorphism? Because f of x plus y is e to the x plus y, is e to the x times e to the y, is f of x times f of y. That's the definition of a homomorphism from an additive group to a multiplicative group. And you can also check f is 1 to 1. Well, you learned that in calculus because the exponential function, the derivative is the exponential function. Positive, function's always increasing. That's what the graph looks like. Every positive real number, take any y, there's always some x where f of x e to the x is equal to 1. And f is also onto. Every positive number is the image of something under the exponential function. So you spend a lot of time in calculus studying the function e to the x, and one of its very important properties is it is in fact a group homomorphism. There's also another function from calculus that goes in the opposite direction. So there's a basic function, g, from the multiplicative group of positive real numbers to the additive group of real numbers. And it's defined by g of x is the natural log of x. Why is this a homomorphism? Well, g of x times y, that's the log of x times y. But you know properties of the logarithm. This is log x plus log y. The log of a product of two numbers is the sum of the logs of the numbers, but log x plus log y, that's g of x plus g of y. So this is the definition of a homomorphism from a multiplicative group to an additive group. In fact, you remember the graph of y equals log x looks like that. It's strictly increasing. and f is in fact 1 to 1. You take two different positive numbers, they have different logs, and onto. Every real number is the log of some positive number. So the functions x goes to e to the x and x goes to log x are in fact isomorphisms of groups. And in fact, they are what we call inverses of each other. Suppose I take the composition f composed with g of x. This means f of g of x. What is g of x? G of x is log x. What is f of log x? E to the log x. What's e to the log x? It's equal to x. So this is the identity. And what about in the opposite order? What is g composed with f of x? That's g of f of x. That's g of e to the x. That's the natural log of e to the x. That's also x. So f composed with g and g composed with f is just the identity function. So I should be a little bit more careful. F composed with g is the identity function on the positive numbers. G composed with f is the identity function on the real numbers. Let's look at another example of a homomorphism. Suppose I let GL2R be the set of all 2 by 2 matrices with determinant AD minus BC not 0. So if A is A, B, C, D, and B is the matrix E, F, G, H, we proved, this is actually a question on the last exam, the determinant of AB is the determinant of A times the determinant of B. So the determinant, this is a function from the set of all 2 by 2 matrices with non-zero determinant to the multiplicative group of non-zero real numbers, positive and negative. Determinant non-zero means different from 0. So this is the real numbers different from 0. 1 is different from 0. The product of two non-zero numbers is non-zero. The inverse of a non-zero number is non-zero. So this is a multiplicative group. This is just multiplying real numbers. And if you take any 2 by 2 matrix with a non-zero determinant, if you map the matrix to its determinant, that's a function from this multiplicative group to this multiplicative group. And this identity says this is a homomorphism. So determinant function, the determinant function, DET, is a group homomorphism. What is the kernel of F? This is all matrices A equal A, B, C, D, which get mapped to the identity. Determinant of A equals the identity. So this is just all matrices with determinant 1. That's what I call SL2R. SL2R means all 2 by 2 matrices with real coordinates with determinant 1. So SL2R is the kernel of the determinant homomorphism. What is the image of this determinant function? Well, if I take A to be the matrix A, 0, 0, 1, this is in GL2R. Because this is a matrix with real coefficients. The determinant of A is A times 1 minus 0 times 0. That's A, not 0. So every real number different from 0 is the determinant of some 2 by 2 matrix. So the image of the determinant is all this multiplicative group. So this group is definitely not 1-to-1, but it is onto. In fact, if I made this AB01 for any B, this determinant would still be A times 1 minus B times 0, which is A. So there are infinitely many matrices with a fixed determinant. What? Any questions? So the exponential function and the logarithm function are really very nice examples of homomorphisms that are important in calculus. And let's look at 1 or 2 more examples of homomorphisms. So first of all, we have the complex numbers. So these are an additive group. We have C star, which is all complex numbers not equal to 0. This is a multiplicative group. Well, you know that the product of 2 complex numbers is a complex number. If they're both non-zero, the product is non-zero and so forth. But you really need to be familiar with the complex numbers. And sitting inside this multiplicative group, we have a set which is usually called S1, which is all complex numbers where the absolute value is 1. What is this? Well, 1i minus 1 minus I. This is the unit circle in the complex plane. It's all complex numbers of absolute value 1. For every t, the number cosine 2 pi t plus I sine of 2 pi t is an element on the unit circle. Why is that? Because what's the absolute value of a complex number? It's the square root of the sum of the squares of the real and imaginary parts. So this is cosine squared of 2 pi t plus sine squared of 2 pi t. But for any angle, cosine squared plus sine squared is 1. So this is the square root of 1, which is 1. And in fact, every point on the circle can be written as a complex number in this form. Suppose I define the function from the real line to the unit circle by f of t is cosine 2 pi t plus I sine 2 pi t. So this is an additive group, and this is a multiplicative group. And I claim this is a homomorphism. I claim the function f from the real line to the unit circle defined by f of t equals cosine 2 pi t plus I sine 2 pi t is a homomorphism. So a claim needs a proof. So this is an additive group. What is f of s plus t for any two real numbers s and t? That's the cosine of 2 pi times s plus t plus I sine of 2 pi times s plus t. So that's the cosine of the angle 2 pi s plus 2 pi t plus I times the sine of the angle 2 pi s plus 2 pi t. And, you know, just like in calculus, you need pre-calculus. In algebra, you also need pre-calculus. You need to know the addition formula for the cosine and the sine. So this is the cosine of 2 pi s cosine of 2 pi t minus the sine of 2 pi s sine of 2 pi t plus I times sine of 2 pi s cosine 2 pi t plus cosine of 2 pi s sine of 2 pi t. That's f of s plus t. And I want to compare that to f of s times f of t. What is f of s times f of t? Well, f of s is the cosine of 2 pi s plus I times the sine of 2 pi s. And I'm multiplying that by f of t, which is the cosine of 2 pi t plus I times the sine of 2 pi t. And you multiply complex numbers, this is cosine of 2 pi s cosine of 2 pi t minus this times this sine of 2 pi s sine of 2 pi t plus I times sine of 2 pi s cosine 2 pi t plus cosine of 2 pi s sine of 2 pi t. And if you look,
Why it's minus?
what? Here,
Why it's minus? Yeah.
I times I is minus 1.
Okay.
Right? When I multiply this times this, I times I gives me a minus 1 times sine of 2 pi s sine of 2 pi t. So this term is this term, and this term is this term. And this term is this, and this term is this. So therefore, f of s plus t is f of s times f of t. So f is a homomorphism. So when I have this function, f from the additive group of real numbers to the unit circle, f of t equals cosine 2 pi t plus I sine of 2 pi t. So we're mapping the line, infinite in both directions, onto the unit circle. We're just wrapping it around and around and around. This is the point 1. Now, it's a homomorphism. So a homomorphism has a kernel. The kernel of f is all real numbers t, such that f of t is equal to the identity in S1. What's the identity in S1? It's just the number 1. So we're looking at all t where f of t equals 1. That means we're looking at all t. What is f of t? Cosine 2 pi t plus I sine 2 pi t equals 1. Which means we're looking for all t where the real part, I mean, two complex numbers are equal, means they have the same real and imaginary parts. So cosine of 2 pi t equals 1, and sine of 2 pi t equals 0. Sine of 2 pi t is 0 for the integers. Cosine of 2 pi t is 1 for the integers. So the kernel is just a set of all integers. So that's really very nice. As you wrap this line around the circle, 0 gets sent to 1, 1 gets sent to 1, 2, and minus 1, minus 2. The integers are exactly the numbers that this homomorphism maps to the identity on the unit circle. So the kernel was Z. So it's always nice to have concrete examples of abstract concepts. So we have the abstract concept of a group homomorphism and the kernel of a group homomorphism. And here's a very concrete example, which you learned in pre-calculus, really. If you assign to every real number t this complex number, that's a point on the unit circle. And it's a group homomorphism by the addition theorems for the sine and the cosine. And the kernel is just the additive group of integers. That's really kind of cool. Okay, well, I think that's a lot for one day. I think the homework number 7 is due on Monday. And there are a lot of problems about groups, and I expect I'll spend all of Monday just going over homework problems and answering questions about both the lecture material and the homework. Any questions before we go?